Okay, so we are our program this year is light, so we have a lot of school lectures and a few only a few workshop talks. And okay, so I'm very happy to have Miguel Paulos, who one of these talks, who's going to tell us about mastering bounds and correlators. Please, Miguel.
Okay, well, thanks to Slava and the organizers for, first of all, for organizing this meeting and for inviting me to speak. So I'm going to speak about how to master bounds on CFT correlators. And so my talk will be based on the paper that appeared in December last year and the more recent one with my student, Szechuan Zheng. And I'll also mention some recent work and ongoing work to go along. So don't hesitate to ask me questions at any point. So I'll start off with some general motivation and the setup. So this talk is about getting some bounds on values of CFT correlators. So then I'll show you some numerical results for d equals 3. Then we'll move on to deriving some exact results for line kinematics. And in the end, depending on time, I'll talk about some applications to study the Regge and flat space limits of correlators. So let me start off with some basic. So here's a picture of the CFT landscape. So it looks a bit confusing because, well, we still have a bit of a confusing picture of this landscape because we can approach it from several viewpoints. This is the most that we can do because this is a very complex infinite dimensional space. And the two different viewpoints that usually we apply are either to get some bounds on the spectrum of allowed CFTs, which I'll call the feasibility problem. So you make some assumptions on the spectrum and then you check whether solutions can exist or on the contrary, you rule them out. Or if you're in a region where the problem is feasible, where you know that there are CFTs, then you can probe this, move around in this space by asking, for instance, what is the largest coupling of some fields among themselves until you reach a boundary. So typically bounds on OP coefficients. And of course, so this fractured picture of the landscape that we have is all the clearer, the better our observational tools. And so this passes through having more computing power, better software applications, and also better functionals. So functionals, it's in the sense that this landscape is really parameterized by our understanding of the crossing equation, and we probe this equation by applying functionals to it. And so if you have better functionals, then we have better information. So here I will propose a new probe.
Miguel,
this probe is simply the allowed values of CFT probe.
Miguel, can you hear me?
Yes.
You are breaking off at times. Can you move closer to the router or shut down some of the other things that take your bandwidth?
Well, I don't think I'm not using anything, and I'm right next to my router.
Okay.
Which should be working.
Okay. Well, let's. As you see, people are saying that the audio is breaking up at times.
But what about my picture? The picture is working well?
The picture is fine, yeah. Well, if there's nothing to be done, then let's just continue.
Okay. So I proposed a new probe. So this probe is the allowed values of CFT correlators. So I think this is a pretty natural thing to consider. So in the S matrix Bootstrap, it has been considered. So people talk about bounds on the value of the S matrix at, say, the crossing symmetric point, because this has the interpretation of some effective coupling. And surprisingly, it had not been considered so far. So this probe is nice because, as we'll see, it presents kind of an interplay or an interpolation between constraints on the spectrum and the OPE. it naturally leads to families of extremal CFTs, that CFTs that saturate bounds, simply because you can ask for minimal and maximal values at different points. So you get families. And there are several interesting regimes to probe. So there's the Euclidean regime, but there's also, so the Euclidean regime is mostly what I'll talk about. But you can go to Lorentzian kinematics, and there you have access to the light cone or double light cone, Regge limits, and so on. So I think it's interesting to explore this. We'll see that in the process of studying these bounds, we'll also end up with some new tools. So something that I call master functionals. These master functionals, they lead to certain crossing symmetric dispersion relations for correlators on the line. Okay, so let's get to it. So, okay, we are interested in studying the space of correlators. So I'll focus on 4-point functions of identical scalars. So I'll mostly talk about this function, G of ZZ bar. So here's a picture of the kinematics. This is U and V. Okay, I'm not writing, but everyone knows what these are. So there's a Euclidean region. There's a Lorentzian region where Z and Z bar independent are real. And there's also line kinematics where Z is equal to Z bar. And okay, so initially you start off in this region 0 and 1, but then you can complexify and go somewhere else. But so these are the basic regions, but mostly will sit here and here. So let us think of the space of correlators. So we can filter this space by delta phi, this dimension, and the space-time dimension. And so here I'm just thinking of this space very basically as the space of identical scalar correlators, consistent with crossing and unitarity of this 4-point function. And so some elementary facts that you can say about this space is that it's like a set of nested Russian dolls, because we know that a d-dimensional CFT is also a d-1 CFT. So any bounds that you can get on correlators in one dimension, they are related to some other dimension. And in particular, if you can, so the d equals 1 case is a bit special, because in d equals 1, this 4-point function only has one independent cross ratio. But so if you restrict correlators in this way, then then any CFT correlator is also a d equals 1 CFT. So if you have bounds in d equals 1, you have bounds in general. So in this space, what are some notable points? So of course, one very notable point is the gap max correlator. So this is simply the correlator whose gap to the leading operator, typically scalar, is maximal. So this is related to this feasibility problem that I mentioned. Another notable point corresponds to maximizing some OPE coefficient. So here I'll consider a very basic case where you impose a gap. You consider correlators which have a gap, delta G, and then you maximize the OPE coefficient of the operator which sits at the gap. Okay, so this we'll see in the next slide. This is basically the OPE coefficient squared. Okay, so inside this space, you can ask, what are these two guys? And so here I'm proposing to study some other extremal points in this space. So there's some G min and G max at point WW bar. And so this is the correlator whose value at WW bar is the minimal possible in the set of all correlators. And similarly for G max. So I should point out that in general, if you make distinct choices of minimizing or maximizing points, then the result will be different. Okay, minimizing at different points in general will lead to different correlators. So another comment is that when you are asking for the maximal, often you want to impose a gap. So this is what the meaning of putting this bar here, delta G. So you are maximizing, you're asking for the maximal value in the set of correlators whose leading scalar, say, has a dimension larger than some delta G. So why do you impose this? It's simple. It's because, So we are only imposing the constraints of unitarity and crossing. And so the normalization of the correlator is fixed by the normalization of the identity. So this is why we can get bounds, why correlators are not arbitrarily small and typically not arbitrarily large. But it can happen that there are solutions to crossing which are unitary and which do not contain the identity. And so in the presence of such a solution, you can always add it to any consistent correlator containing the identity, and you can add it with an arbitrarily large positive coefficient, and so there will be no bound. Okay, so this may happen. So sometimes you need to impose a gap. This is the majority of circumstances, but sometimes you will also be able to get a bound which is independent of the gap. Okay, so let's try to get some intuition for what to expect for these minimal and maximal correlators. So to do this, we're going to use the OPE. Okay, so phi with phi contains these operators with even spins. And the correlator is expanded in terms of conformal blocks like this. So this is just the unitarity bound. So the OPE coefficients, this is what I was mentioning before, are just the OPE. These A's are just lambda squares. And so now let us think of what does the OPE look like for one of these minimal or maximal extremal correlators. Since these correlators, they are extremal, so they saturate some bound, we expect their spectrum to be sparse. Okay, so when you look at the OPE, you will not see, you'll see well separated operators. And so this is why this expansion makes sense. And in particular, we can think of approximating these correlators by their leading contributions, which are the identity and the first operator, which here for simplicity, I'm assuming to be a scalar. Okay, so R here is what I call the radius. So I'm using the radial coordinates of Matthijs and Slava. And so R is just the norm of rho. Okay, so for small r, this expansion holds. Okay, so now let us see, what do we want to do? We want to either minimize or maximize the correlator. So how can we do this? If we want to minimize, clearly, since this radius will be smaller than 1, what we want to do is that we want to maximize the gap and to some extent also minimize the corresponding OPE coefficient. Conversely, if we want to maximize the correlator, then we want this gap to be as small as possible. And then we will want to maximize its OPE coefficient. Okay, so this is the rough intuition. To minimize, you want to increase the gap, and to maximize, you want to lower the gap. So minimizing correlators will have large gaps, and maximizing correlators will have small gaps. And so we expect roughly, at least for small r, then the minimal correlator should be closely related to the gap max correlator, and that this G max under a gap assumption should be closely related to the OPE max correlator. So this is the expectation. It's not always true, because even this heuristic argument, it depends on the exact value of R, and there can be other contributions and so on. But in many cases, it turns out that this will be correct. Okay, so now let me explain how we can actually get bounds. So as usual, we're going to use the crossing equation. Okay, so these F's are the usual crossing vectors. It's just the conformal block minus its cross-channel image. So the crossing equation for the correlator looks like this. So I'm assuming that the scaling dimensions and the spectrum, they live in some set S. You know, usually this set S is very broad. We just assume that there is a gap or something. And now if we want to get a bound on the value of the correlator, we can do it as follows. Suppose that we have linear functionals that will act on this equation with the following properties. So these linear functionals, they are labeled by some parameters, W and W bar. So I apologize, it might be a bit confusing. These are really parameters where here they were variables for the crossing equation. So I'm going to choose a minimizing point labeled by some choice of W bar. And I'm going to ask for this functional to satisfy the following constraints, that when it acts on the crossing vector delta L, it should be larger or equal than, well, minus the conformal block delta L evaluated at this W and W bar. Okay, and similarly for this guy, which will give us an upper bound. So we are used to imposing basically that functional should be positive, should be non-negative in some region, but actually when you want to do OP maximization, sometimes you need to assume that this functional is larger than -1 or something like this at a particular state. So this is what you would write indeed in a problem where you're doing some OP maximization, where the OP coefficients, they are weighted by the conformal blocks, which is of course what we want to do, right? So minimizing or maximizing the correlator is simply an optimization problem for the OP density, where the OP coefficients, they are weighted by the conformal blocks. And so in the dual picture of the functional, the constraints look like this. And so indeed, it's very easy to see that if you take a functional satisfying these constraints and you act on the crossing equation, then you get bounds that look like this. Okay, so this is the identity, which we had to separate. And okay, so these are the bounds. And so our goal should be to impose these constraints and maximize the action of the functional on the identity. So as a very trivial example, but just to get a notion for this logic, let us define the functional that when it acts on a crossing vector, it gives minus the crossing vector evaluated at these points. Okay, so this is my choice of functional. Clearly, so this is a good choice because it satisfies the constraints. The constraint is that it had to be larger than this piece. And since this is a positive object, it's W bar in the Euclidean section, then I'm satisfying the constraints. And so this functional will give us a bound. It will give us a bound. I just need to evaluate the functional down the identity and add up the identity block, and I get a bound. And in this case, the bound is trivial. So it just tells us.
So Miguel, shouldn't there be some extra factors in the right-hand side? Because F is like block times something which depends on delta phi.
Yeah, the delta phi dependence is here. Actually, sorry, there's a typo. There should also be some bar delta phi here. So my blocks are defined such that the dependence on delta phi is inside the blocks.
Okay.
Okay. And so the bound in this case, this just tells us that the correlator has to be larger than this, but this is what? It's just the identity in the by crossing, you can get similar bounds in the other channels. So this is just a trivial statement that the correlator is a positive sum of blocks in each channel, and we know that one of these blocks is the identity, and hence the correlator has to be larger than that block in any of the channels. Okay, so it's an obvious bound. So, but this is just to show that you can get it by using this functional logic. Questions? Okay, if not, so let us now discuss the numerics. So, yeah, sorry, this should not be lambda, this should be omega. Sorry for that, so this is omega. So the setup of our problem is we want to maximize the action of functional omega or lambda on the identity subject to these constraints. And we're going to maximize over some search space L. And this search space here, I'll just take it to be the span of a finite dimensional set of elementary functionals, which I'll just take the usual derivative basis at the crossing symmetric point. And we solve these linear programs with Julius. So here's the first set of results. So there's a bit to unpack in this plot. So let's go slowly. So here we have the external dimension, delta phi. Here we are considering the value of the correlator at the crossing symmetric point. Okay, this is A hat. Here's the definition of A hat. It's just for convenience. And so as you see, so there's both an upper bound, which is this topmost curve, and there's a lower bound, which is this bottom curve. Okay. So the upper bound actually it diverges at some point. And in fact, it's easy to see that it has to diverge at delta phi equals 1. The reason for this is that when delta phi equals 1, you can consider the phi squared correlator in free ON theory. And that correlator has a piece, which is of the form that I mentioned, which is a unitary solution to crossing without identity and with a coefficient that you can choose, basically. And you can make it arbitrarily large. And so there can be no bound when delta phi is larger or equal to 1. So these other curves are the upper bound that you get if you impose a gap. So this is when the gap is delta phi, 3/2 delta phi, and so on. And so here, even though we didn't write it, so what is this curve, this dashed curve? This curve corresponds to the correlator given by the generalized free boson. Okay, the generalized free boson, well, if you restrict it to the line, it looks like this. Of course, we know how to write it even away from the line, but this is what it looks like. And in fact, if you impose a gap equals to 2 delta phi, which is the dimension of the first operator in this correlator, then the bound will be saturated by the generalized free boson. Okay, so that's the first thing. So as you come down from the bound, eventually the upper bound meets the lower bound, and they meet at the kink, which is just free theory. And then, okay, this is the lower bound curve, and the lower bound curve is kind of funny because, you know, so if I had flipped it, it would look just like the bound on the leading scaling dimension for 3D, right? So there's some rising region in there, a different slope, and there is a kink, and this kink turns out to be saturated by the 3D easing correlator. Okay, so we'll see this better in the next slide. But you know, this is according to this discussion that I told you, that we expect that correlator minimization can be related to gap maximization, and we know that gap maximization is saturated by 3D easing. The other observation is that this lower bound is always above this black dashed curve, and this black dashed curve is what's known as the generalized free fermion. Now, this generalized free fermion is a purely 1D solution. It does not exist in higher dimensions. Here we can compare to it because we are evaluating at the crossing symmetric point where z is equal to z bar, so it makes sense to plot it. But in general, I wouldn't know what to draw. But nevertheless, you see that the bound is always above this curve, and it seems to approach it very fast. So I don't have a good explanation for why the bound in 3D rapidly approaches this curve. It would be very nice to get an explanation for this. However, what we will be able to prove is that this curve has to be above this one, because this is actually an exact lower bound that you can prove. Okay.
Can I ask a question, Miguel?
Yes. I'm not hearing you very well.
Okay, so is it better now?
Yes.
Okay. I did not understand why the upper bound cannot exist above delta phi equal 1. You gave an explanation for delta phi equal 1, but why does it imply also for larger delta phi?
Because for larger delta phi, you can just take a generalized free field with ON, for instance.
And this doesn't work for smaller delta phi then?
No. If you try for smaller delta phi, it will violate unitarity.
I see, thanks.
So basically, I mean, there's just an explicit correlator that you can write down, and you can decompose it into blocks, and there is no identity, and when you look at the OPE, it will be unitary and not unitary if it's below 1. So you know that this has to diverge at 1, best case scenario.
Okay, thank you.
For the generalized free fermion, are you considering the operator psi bar psi or just psi by itself?
It's just psi.
Right, so it's a spinless fermion, basically.
Yeah, it's a 1D fermion, yes.
But what you said that we can prove that this numerical bound has to lie above generalized free fermion, but is it a hard proof? Because it seems to be pretty clear. You just stick to the line. As you said, the space of correlators belongs to the space of 1D correlators. So this seems to imply this bound.
No, well, no, because I mean, in 1D, what there is a proof is that the gap max correlator is the fermion. But you still need to prove that the minimal correlator is the fermion. It's not the same thing.
No, what I mean is that, okay, we are minimizing within correlators. So the 3D correlator Oh, okay. Okay, sorry. I take it back. Yeah. Yeah, we have to prove something. Sorry.
Yeah. So this is just to make this statement that so now I'm looking at upper and lower bounds as a function of z. So I'm plotting the correlator normalized by this funny 1D fermion solution because it's convenient. And so delta phi here, I take it to be the Ising delta, so 0.518. So for this case, there is both an upper and lower bound. So any 3D CFT correlator has to live here in this blue region. And so you can see that there's some red dashed line here, and that red dashed line is the 3D Ising correlator. So this is telling you that indeed for any choice of Z, the 3D Ising correlator is the smallest correlator allowed, basically. So we expected something like this to be true if Z was sufficiently small because of this heuristic argument that I gave. But here it's really telling you that it holds all the way to Z equals a half. So this is yet another bound that's saturated by 3D Ising.
Miguel?
Yes.
Hi. Can you say a little more detail about that line? It's exactly on the lower bound for the entire range, or there was like a tiny little sliver, or
Well, I'm going to show you. Yeah, I'm going to show you exactly. Yeah.
Okay, thanks.
It's so you can see it in this slide.
Thank you.
So now you can ask, yeah. So gap max and colonization, they seem to be very close, but how close? And so a proxy for this is to compute the difference in scaling dimension of the leading operator, okay, as a function of delta phi. And you see that this difference is very small. It's very small, and in fact, it's minimized here at the Ising point. Okay. So you may recall a similar plot that was done when we were looking at gap maximization versus C minimization when discussing 3D Ising, and there was also some very small difference between the two. So here it's similar. So it seems like we have yet another measure that's pointing at 3D Ising. And they agree closely, but okay, we don't know. Maybe there is some tiny difference that's impossible to get rid of. I mean, we cannot tell. But in any way, it seems like a very good proxy for determining where the 3D Ising solution lives. And in fact, so I should say that this is actually, you can turn this into a useful statement. So I'm not going to go into detail here in the talk, but this statement that correlator minimization agrees with gap maximization is very useful for numerics, because when you're maximizing the gap, typically you have to search, you have to do bisection, or you have to navigate, or whatever. So here this is telling you that there is a single optimization problem that you can solve that will give you gap maximization on the nose. And in fact, you don't need to do correlator minimization. You can cook up some similar looking optimization problem that you can use to get really the gap max solution to whatever 15 digits or whatever in a single run. Anyway, so this agreement holds here in some region, but eventually it breaks down. So here I'm showing you the leading operator in the spectrum for the gap max correlator, and then for the minimal correlator depending on various choices of minimal points. Okay. So all these curves lie on top of each other for a while. But then there's some delta phi, more or less, around 1 point something, where all these curves split. And so why does this happen? It happens because this happens precisely at the point where the dimension of this leading operator hits around 3. And 3 is the dimension of the first operator in the spin-2 sector. So I told you that to minimize the correlator, you want to push up the gap. But which gap? Because there are many spin channels. And so this is a circumstance where the gap is around 3, and so there's a competition between the leading operator in the spin-2 channel and the leading operator in the scalar. And you want to push up the gap, but there's a competition between the two. You don't know exactly how much you push one or the other. So our heuristic approximation in this case looks like this. So there are two competing operators where delta G is approximately delta T. And so depending on the precise choice of angle and R, you get a different answer and you'll get a different correlator. So in this region, you really get families of CFTs. Now, maximization. For maximization, so here this is a plot where I'm fixing delta phi, and I'm varying the gap. And I'm making a comparison between maximizing the correlator, which is the blue line, and OP maximization, which is the gray dashed line. And so as you can see, if the gap is sufficiently large, so sorry, and again, I'm bounding if the gap is sufficiently large, then both problems actually agree, or they agree very closely. And the reason for this is easy to understand. It's because in this case, so you want to maximize the correlator, so you want to both maximize the OP coefficient and minimize the gap. But so if we look at the plot of the maximal OPE coefficient, then you see that it's increasing. As I lower the gap, I can get to higher values. And so both things push in the same direction, which is to lower the gap. And so both computations will agree. But eventually there's a peak here, and then the OP coefficient starts going down. And so the OP maximization will follow this curve, but correlator maximization will not. So in this region, we will have again get a competition between effects. And depending on the choice of point, you get different correlators. But here they all agree, and in particular, they agree with OP maximization. And so again, we see that when the gap is 2 delta phi, well, I didn't tell you what delta phi is, but you have to believe me that this corresponds to 2 delta phi. The bound is saturated by the generalized free boson. And in fact, you can even look at deformations of the generalized free boson. So these are parameterized by lambda phi fourth in ADS, basically, and our bound is saturated even perturbatively around generalized free boson. So it would be interesting to explore this a bit further, but that's a different story. So in the region, when we don't put a gap, as I told you, the correlator that maximizes depends on the choice of point. So this plot is supposed to illustrate this. So I'm dividing the correlator as a function of R prime for different choices of R. So different choices of R correspond to different curves. And then I'm plotting that correlator as a function of R prime. And then I divide by the envelope, okay, by the maximal for all R. So they have to always touch 1. And so this correlator is maximal at this particular value of R prime, and the green one is maximal at this value, and so on. But in general, so you get a family of correlators. And so one thing that you can do is, well, let me ask about the small R limit. Okay, so let's take this family of correlators and let's take the limit where the maximizing point goes to 0. So what do we expect? We expect, so since we are lowering R, we want to lower the gap. We want to lower the gap, but there's the unitarity bound. So our leading operator gets pushed down to unitarity. But at unitarity, the OP coefficient has to go to 0 because it's a free field, so it cannot couple to some non-trivial external field. And so in this limit, something funny happens, which is that so the operator gets pushed down to unitarity, and the OP coefficient goes to 0 in such a way that there's a finite limit. And in particular, it's this limit. So the conformal block, when you take it to unitarity, it blows up. But then this blowing up gets canceled by the OP coefficient, and you get a finite contribution of a different state of dimension 5/2. Okay, so the effect of this operator at unitarity is mimicked by mimics this operator at 5/2. And so one natural thing to ask is, well, maybe this limiting correlator is simply doing OP maximization at delta equals 5/2. And so this is what we checked, but then there is a surprise. So the blue dots are correlator maximization at 10 to the minus 600, so very small. And the gray dots, which mostly you cannot see because they lie on top of the blue dots, are this OP maximization at 5/2 that I mentioned. So both correlators indeed seem to agree. And you see that here's an operator at 5/2 for OP maximization, and then here there's this guy at unitarity in correlator maximization. So these ones, of course, they will appear separately, but all other operators seem to closely match. But then there is a surprise, because if you put in this plot also the spectrum of gap maximization, which a priori has nothing to do with this story, then all three spectra seem to coincide around 0.505. Okay, more or less here, depending on how you define it. So recall, gap max corresponds to the easing here. So here's the easing kink, for instance. So this drop corresponds to the operator epsilon prime, which has dimension 3.84. It starts off here and then it drops down. And then so this 3.84 guy is going to become this 5/2 guy. So there seems to be some special solution to crossing here, which is characterized by the fact that it maximizes the gap and maximizes an OPE coefficient and maximizes the correlator in this funny limit. And it has a protected operator of dimension 5/2. So it would be very interesting to try to explore to see if you can put this theory on an island or something like this. Okay, so that's the end of this numerical results. So questions about this? Okay, so then let us discuss now how to get exact bounds in line kinematics.
I have a question. So in the
very
case of C-minimization, I have a question. Can you hear me, Miguel?
Yes.
So in the case
Yeah.
of C-minimization, which is another way to get the easing, we had to actually impose some additional gap condition on the spectrum. I don't remember which one, but delta epsilon had to be slightly above. I don't remember what, like it has to be slightly above 1. I forgot. It was some robust condition that we had to impose that, you know, for the C-minimization to be valid.
Yes.
So in the case of this correlator minimization, it's just like within all. Do you have to impose any condition apart from unitarity bounds, or is it just like this on the nose?
You just get it on the nose. There's no assumptions.
Okay. Cool. Nice.
Okay, so let me discuss exact bounds on the line. So I'm going to restrict to these kinematics where z is equal to z bar or w is equal to w bar, and I'm only using the constraints of SL2R. If you want, I'm only using the constraints of the 1D conformal group. The results will, of course, apply to correlators in general dimension. They will not be as strong as they could be, but anyway, I want to keep the discussion general, so I will not. Any correlator can be expanded like this, and there will be relations among OP coefficients, but I will not use these relations. I will just assume that all these coefficients are independent. And the conformal blocks, they take a very simple form. Yeah, so there are several restrictions to the line. I'm considering the restriction which is analytic between 0 and 1. So our expectation is that the minimal correlator is the gap max correlator, as I mentioned. And in 1D, it has been shown that gap maximization is saturated by this free fermion solution. Okay, the free fermion solution, if you decompose it into blocks, it takes this form. So it has a spectrum of double trace operators with dimension 1 plus 2 delta phi plus 2n. And so the bound, you find that it's saturated by a theory which contains an operator of dimension 1 plus 2 delta phi, which is nothing but this n equals 0 gap. And so we would want to prove that any correlator has to be larger than this correlator. This is our goal. So how can we do this? Well, recall that to get these bounds, we have to have a functional that has to satisfy some constraints. Okay, so if this functional satisfies these constraints, then you get this bound. If the bound is to be saturated by this generalized free fermion, then these constraints will have to be saturated whenever you act with the functional on this fermion spectrum. Okay, so when you act with this functional at these values of dimension that I mentioned before, the constraints have to be saturated. It's very easy to see that. So if you impose this, then it's very easy to show that the action on the identity is given by the generalized free fermion correlator. And so if you plug this result here, you get the desired bound. Okay, so this is a necessary condition. A bit less intuitively, you also need to impose this condition of saturation on the derivative. Okay, so to understand this, you just take this guy and you put it on the left-hand side, and then these are just some positivity conditions. And so this condition is basically just saying that if this positivity touches 0, you want the 0 to be a double 0, so that positivity is maintained. And so you need to also impose this condition on the derivative. Okay, so these are necessary conditions. They are not sufficient to guarantee positivity everywhere, but they are necessary. And so what we're going to do is that we're going to solve these conditions by using a functional basis. Okay, so this is introduced by myself and Dalimil a few years ago. So there is a statement that the crossing equation in one dimension is completely equivalent to the vanishing of some sum rules. Each sum rule is given by a functional contained within a basis. And this basis contains functionals alpha and beta, which are precisely dual in some sense to this generalized free fermion solution. So if you satisfy all the sum rules here with omega replaced by alpha and beta, then this is the same as solving the crossing equation. So this is like a complete. So this is a functional, so it's very natural to write this functional in this basis, and using these duality conditions, you can find the solution. Okay, so this I call the fermionic master functional. So why? Because it tells us that this function in a sense is some kind of generating function for this functional basis. Okay, so if you write this function like this, then it will solve these conditions. Okay, so this is our solution. This is our proposed exact functional that will give us the bound that we want.
But is it a good functional?
Well, yeah, okay. Well, I'll discuss this, of course, because there's an infinite sum. So you have to worry. Right? The finite sum to be fine, because all of these guys are good functionals. Yes?
Yeah, I have so this problem that you're discussing, the minimizing of correlator is, yeah, indeed looks like very natural from the CFT point of view. But in principle, we could consider some problem where we would minimize something else, like some other weighted sum of p coefficients. And in this language, it would just correspond to replacing coefficients of this functional to some by this something else.
Yes.
So it looks like, if I'm not mistaken, it means that your method actually provides this candidate extremal functionals for a gazillion different minimization problems, not just this. So this sounds like too good to be true. So it must be some catch. Is there something special about these coefficients that you're considering?
Yeah, of course. The catch is that these are only necessary conditions. They are not sufficient. So sufficiency is positivity even away from those guys.
Okay.
And so indeed, if you cook up some random minimization problem, you solve it like this with some coefficients, then these necessary conditions will be solved. But then if you plot the functional, actually, you'll find that it will have negative regions, for instance.
Okay.
In this case, it will not.
Okay.
So let me just mention that we can do the same thing for correlator maximization. We can play the same game. So now we're going to demand an upper bound on correlators with a gap. And this gap, I'm going to set it to be 2 delta phi. Because we saw in the numerics that there seemed to be an upper bound saturated by the generalized free boson. So we're going to try to prove that one as well. And so it's the same story. So there's also a bunch of necessary conditions that you need to solve. If you solve these conditions, then the correlator will be smaller than the generalized correlator. And again, we show that there is a basis which is dual to that solution. And so we can solve for this functional. So here's a different master functional where now we just replace B with F. And so this functional is a candidate for establishing this bound.
So
now regarding Slava's question, how do we know that this is a good functional? So one way to show that it's a good function is just to construct it independently of the basis. Okay, so let us just construct a functional that satisfies these necessary conditions, but where we make no reference to this basis. And to do this, so we just write this functional in the usual ansatz. So for people who are familiar with this functional story, so this is an ansatz for the functional. So there are two kernels, G and F, and that the action of the functional in the crossing vector is defined by these integrals. So all of these functionals, alpha and beta, they take this form for specific choices of G and F. And the distinction in this case is that this G will usually contain a delta function that is not present in these cases. Anyway, I don't want to swamp you with details. I'm just telling you that there is a way of choosing functionals such that choosing these kernels such that, for instance, you can show basically by deforming the contour, functional actions look like this. The functional actions look like this. And the key point here is that you get these cosine squares and sine squares, right? So if you compare these with the positivity conditions, so omega minus G has to be positive. So omega minus G has to be positive. So if this kernel is positive, it will be golden, okay, to be positive. And furthermore, this guy automatically has double zeros, which is what we want. We want these double zeros here at the right places, okay? So this is one of the constraints that we need to impose on the kernels, and there are other ones. These other consistency conditions, they guarantee that this is a good functional, which is what Slava is worrying about. And you can just solve these constraints for the kernels. So here's an example. So various solutions depending on values of delta phi, and you can take this delta phi to be whatever you want. So these are not like integers or anything. These are just some random values. And the observation is that these kernels turn out to be positive. And so it means that these quantities, so these inequalities, they will be positive even away from the double zeros. Okay, so we require these double zeros. These were necessary conditions, and now we almost have sufficiency. Okay, because this whole thing is positive actually for any delta. The only reason why we're not done yet with our bound is because this representation of the functional action requires some constraints on delta. But for instance, if delta phi is smaller than 1/2, I just proved the bound for you, because then this representation is always valid. Okay, but basically, morally, this is why the bounds are true. It's because of this. There's just some discrete checks that have to be made now. So I'm going to come back to those. But so let me take a detour through a different story, which is the connection of these functions to the Polyakov bootstrap. So you look at this functional, you stare at it, and it reminds you of our Polyakov blocks. So Polyakov blocks are crossing symmetric sums of Witten exchange diagrams with specific choices of contact terms. And if you take this sum and you expand it in conformal blocks, you find that they take a form that looks like this. So there's a G delta, and then there's a sum over double trace operators. And if you choose these contact terms appropriately, then it turns out that the coefficients are precisely these functional actions. Okay, so this is a story that we explained a few years ago. And so you come to the nice conclusion that there is a connection between these master functionals and Polyakov blocks. Okay, and the connection, the precise connection is given by this. And so if you use this connection, then you get a very nice result, which is that the sum rule of the master functional is equivalent to validity of the Polyakov bootstrap. Okay, so this is not a new thing. So the demanding that the Polyakov bootstrap holds is exactly equivalent to demanding that this single functional provides a good sum rule. Okay, of course, here it's a function of W, so you have to import for several values of W. So there's this nice link. Furthermore, this sum rule, recall that the functional action took this nice form with these cosine squares. And so it's easy to see that using this relation with the Polyakov block, that the Polyakov block is actually computed by this. So this thing on the right-hand side is the Polyakov block. So this is one way to compute the Polyakov blocks. And so the statement of the Polyakov bootstrap then becomes following. Okay, these equations are, you can think of them as dispersion relations for CFT correlators on the line. Okay, so they involve these kernels that depend on the master function. So there are two dispersion relations because we have this fermionic and bosonic basis. So this is the double discontinuity, the bosonic one, the fermionic one, you just flip a sign. And the dispersion relation holds for subtracted correlators. And here's the definition of the subtracted correlators. So you have to take your correlator and subtract all the Polyakov blocks for which this integral representation was not valid. Okay? But importantly, so you need to do these subtractions, otherwise these integrals will not converge. But importantly, the number of subtractions is finite. Okay? And so in presence of a gap, for instance, you can even reduce them to just one. So there's always one that you need to make, which is the contribution of the identity. And then there will be some finite number of ones, depending on your gap. And so I emphasize that this actually holds for any CFT correlator, not just one CFT correlator. So maybe this was a bit fast. Are there questions about this?
Okay. Maybe I can ask a question. So you say that this holds for any CFT correlator on the line, of course, because you have a single variable. Do you think there would be any way to also do something with the other variable if you have a high dimensional CFT correlator, like take like coefficients of the series expansion in whatever W bar minus W, something like that? Is there any way, or look at the full correlator one spin at the time? I'm just throwing out some crazy ideas that obviously don't work. But is there something like that that you think could work?
Right. I tried to do something like this, but I failed. I couldn't get it to work.
I see.
I would just like to say that in 2D, because of holomorphic factorization, you might be able to write down like a product of these things. But well, okay, I haven't thought very carefully about this. Yeah, I'm not sure.
Okay, thanks.
But maybe at the end, so I mean, there are some dispersion relations, of course, that have been written down for higher dimensional CFTs, where they involve the two cross ratios.
Sure.
And so the only nice thing about this one is that you lose the dependence on the two cross ratios, but what you gain is this finite number of subtractions, which in general is not true. In general, in high dimension, you need to make an infinite number of subtractions. And yeah, maybe I'll comment on this at the end. Okay, so let me discuss some applications. So bounds, okay, let me go back to proving the bounds. And so the proof in this case, well, it's not a rigorous proof, but basically it boils down to the fact that these objects have a definite sign. Since these objects have a definite sign, it follows that these G underline and G overline, they will have a definite sign. And so what you can establish rigorously is this, okay, these inequalities. So these bounds are definitely true. And in particular, so let's look at the upper bound first. Clearly, if you have a gap up to 2 delta phi, then these terms are not present, and then this implies the bound that we wanted to prove. Okay, so that's good. For the lower bounds, well, in this case, it's hard. So the Polyakov blocks that live below this threshold, we don't have a good integral representation for them that manifests positivity. So the only thing that we can do is that for any choice of delta phi, we can just like plot them and see their sign. And in every case that I've checked, they are positive. And so since they are positive and this is a lower bound, you can just drop them to get the bound that you want. So it would be nice to get a more rigorous proof, but okay, at this point, I don't know how to do it in any other way than this, just by plotting and checking. And of course, if you have some information on the correlator, these bounds, they give you a stronger version, right? If you know that there is an operator sitting below the gap, and you know the OP coefficient, then you get a stronger bound than what you would otherwise have got.
Can I ask
So
a question about this?
yes.
I'm probably getting this wrong, but in the initial plot, it seemed the bound was getting very, very close to be saturated with the free fermion correlator was getting very close to be saturated on the right. I think it was delta phi on the
Yes.
x-axis. So this means that this A delta have all to be very small in those cases. Is there some understanding of this saturation? Right. I mean, here you have a bound in which there's some. It's the bound is strictly above if the Polyakov block are positive in the first line, if you have these operators below 2 delta phi minus 1, and yet in your first plot it was going very close, so it means that all these contributions were very small. Do you understand this?
Well, so there are two things. So first of all, in that case, I think those terms are simply absent because the gap is large. Yeah, I think those terms will be absent because the gap will be larger than 2 delta phi minus 1. So it's just that this inequality is not saturated in that case because the correlator has further constraints because it's a 3D CFT correlator. So
right. But that I understand. But the fact that these are absent is it clear? Is it just some feature of the minimum correlator that you're finding with the bound or the Bootstrap bound, like some consequence of sparseness, or is it clear that they should be absent?
Well, you are maximizing the gap. So as long as the gap is above 2 delta phi minus 1, then okay, these things will not be there.
Okay.
For me, the real puzzle is then why is this so close to being saturated? It's telling you that in some sense there is a way, at least maybe when delta phi becomes probably infinitely large, there is a way of extending this solution away from the line. The solution only exists on the line. So there must be some funky solution that you can extend, and which coincides with this, probably at infinite delta phi only. And that would explain this bound. Okay, so now I think I'll Regge. I'll talk about the flat space limit, which it's a bit more fun. Okay, suppose that now that you have a family of 1D CFT correlators, or a family of CFT correlators on the line, but okay, let's think of this case for definiteness. So this could arise, for instance, by putting a quantum field theory in ADS2. And so you get a family because you can tune the ADS radius. So of course, there's many other previous works, but in recently with Balt and Shota and Xiang, we made this proposal for extracting the S matrix from the correlator. And this proposal is a bit simpler in 2D. Basically, it just says that you can get the 2D S matrix almost directly from the correlator after you identify kinematics appropriately. But so you need to take this flat space limit. So this is like a flat space limit operator. And what is this flat space limit? You can think of it as consisting of two steps. So first of all, you go into some region where you can take the limit delta phi to infinity and get a finite result. So I should say that the flat space limit corresponds to taking the limit where all the scaling dimensions are large when you have a gapped QFT in ADS. So the flat space limit is this limit. So in the first step, again, you go to some region and you take this limit, and then you analytically continue into the region where the limit does not exist. And so, for instance, let's take these free field correlators as an example. Then if you take the large delta phi limit of these correlators, then you either get 1 or infinity, depending on the region. Okay. So if you're outside these black disks defined by these inequalities, then you get a finite smooth limit. You get 1 or plus or minus 1. And here, well, you don't know what happens. So your job now is to analytically continue into the inside of these disks. And okay, in this case, it's trivial. It was just 1 on the outside, so you can just smoothly continue and you just get 1 everywhere. Okay, so 2 steps. But so in general, how do we do this? Like if you just given some general correlator, where do you know where the limit exists, and how do you do this analytic continuation and so on? So in our paper with Balt and so on, we showed that, for instance, in Mellin space is a good way for doing this analytic continuation. So here I'm going to propose something different. So this is based on work with Lucia Cordova and Yifei He. And the key fact is that these subtracted correlators that we discussed, they have a very simple flat space limit in that they require no analytic continuation. So these subtracted correlators, the flat space limit is simply the large delta phi limit, and this limit exists, okay? So this means that this object, G bar, when you take delta phi to infinity, is a smooth analytic function in the cut plane. And so we're going to do a split. We're going to split the correlator into the subtracted correlator plus the subtractions. And so the flat space limit of this guy is easy. And it turns out the flat space limit of these guys is also relatively easy. So the S matrix decomposes into two pieces, this piece and this piece. So this piece is the part of S which is analytic in the cut plane, and it receives contributions from all states above threshold. So for instance, you can use the dispersion relation that I wrote down, the CFT dispersion relation. It literally becomes the dispersion relation for the S matrix, the usual one. And you can show that, for instance, the double discontinuity of this G bar is simply the imaginary part of the scattering amplitude. So this guy is analytic. Then you have to discuss the flat space limit of these subtractions, and here it's less trivial. So what you can show quite easily is that each term in this sum, the flat space limit, you can compute it because we know what these Polyakov blocks are. So you can just, and there are bounds on this OP coefficient, and they give you what you expect. Basically, they give you contributions of bound state poles. So you see, these guys now, they lead to non-analyticities in the cut plane. So the issue that we're currently trying to make some progress on is that, so if there is a gap in the spectrum here, if you know that all the states begin above, the exact number is square root 2 of delta phi. Anyway, there's some thresholds. If all the states begin above that state, then we know how to compute this flat space limits, and everything works. You can get the S matrix. You can prove analyticity. You know everything, basically. You can prove that it's analytic on the cut plane. At most, it has singularities on the real axis, and you can characterize them. You can characterize everything purely in terms of the CFT data. The problem is that if there are states below this threshold, then it seems like you can say nothing, because this threshold is the threshold basically where these solutions to crossing without identity can appear. And so they screw up all possible bounds that you can have. And of course, this threshold is precisely, in S matrix language, it would correspond to being able to have anomalous thresholds. So if the circumstances where you have anomalous thresholds in the S matrix are precisely the region where all the CFT bounds basically break down. And so we cannot say anything. So we're trying to think what conditions we could impose so that we can say something. Okay, so I'm going to skip the Regge limit, just move on to the outlook. So first of all, one idea is that it might be interesting to use this dispersion relation or some other one, or equivalently the Polyakov bootstrap, for doing numerics. So maybe it's worth revisiting the bootstrap in position space, but now where you use this dispersion relation basis. So one reason for optimism is that, so there's this observation that if you take the 3D Ising correlator on the line, so this is the blue line, then you can approximate it very, very well, like to 1 part in 10,000 as just a sum of 2 Polyakov blocks. Okay, so you just take the identity and you take the epsilon. So this is like a souped up Polyakov block where you take into account the descendants, the d equals 3 descendants. But anyway, morally, it's just a sum of 2 Polyakov blocks. And there's even a way to tune this coefficient so that it's not an independent parameter. But you see that it's a pretty good approximation. So I think to me, this is telling us that this kind of functions can be very useful even in high dimensions. The other thing is that we cooked up this dispersion relation for the correlator, and it seems very natural to generalize it where you have many correlators at the same time. So now you want to express the correlator in terms of the double discontinuity, and there will be some kernel. And this kernel, one way to think about it is that it's the unique function whose double discontinuity is basically 1, okay, it's some delta function. So I did this in my original paper, and recently we showed that this logic is correct in the case where all fields are related by global symmetry in 1D. So this is work with Kaushik Ghosh and Apratim Kaviraj, and we even got some nice bounds for ON theories, correlator bounds again at the crossing symmetric points. And okay, maybe I'll just conclude with some open questions. So we can ask, going back to these numerical bounds, is there some extremal CFT that we've missed? Can we find other interesting things in other dimensions? Can we use this logic to study the light cones and double light cones limits for correlators? It's a bit difficult using numerics because these limits, they probe a very large spin. So it seems like there's an order of limits between having many derivatives and having many spins. Can we get better bounds on Regge? And okay, can we prove this GFF bound in higher D? Because I only proved it on the line, but it looks like it's true even away from the line. And this, I think, will require working with some different dispersion relation or Polyakov blocks. And, okay, maybe some exact bonds in equals to. That's it. Thank you.
Thanks, Miguel. We have time for questions.
I have a question, Miguel.
Yes.
So you mentioned that the fermion bound, lower bound, can somehow be very close to the 3D Ising CFT when delta phi is large enough.
Not 3D Ising CFT.
Oh,
the 3D lower bound.
The 3 lower bound, yes. Yeah, exactly this one.
Yes.
You were commenting that maybe
yeah.
When delta phi is large enough, maybe when it's infinity, then the 3D CFT can really coincide with the lower bound. And then this would sound like some flat space limit.
Yes.
But on the other hand, you were saying, as we know that if we take the full correlator and take the flat space limit, there can be some blow up or divergences there. So these two pictures seems not, I don't see how to place these two pictures together. Or to put it another way, like, is there a hope to get some bounds of the flat space S matrix through this observation?
Sorry, I mean, indeed, you're right. So in this case, the correlator will blow up. It's just that they blow up at the same rate, basically.
Okay.
So yeah, so you're asking if I study the difference between these two correlators. I think this is what you're interested in, right?
Yeah, I'm saying that using this 1D bounds, when delta phi is large enough, it can really tell us something about the higher dimensional CFT, or more precisely the flat space S matrix, because we're taking the flat space limit.
Right. I'm not sure. I think in that case, what you want to bound is like subleading correction. So in higher D, probably the statement is that the flat space limit, all correlators look like the generalized free boson plus some suppressed corrections, right?
Yeah.
And then I'm not sure I can say something about the size of these suppressed corrections. Well, I haven't thought about it in any case.
Okay,
it's
yeah,
true that in 1D we can, I mean, in 1D we can get bounds even when the gap is not to delta phi. We can take it a bit below, and we can compute these things in perturbation theory. Yeah, this is a proxy for the theory not being free, so it might help with what you're saying.
Okay, yeah, I need to think about that. But anyway, it's a very vague question. Thanks.
So if I understood it, you had a prescription for going from a 1D CFT to a 2D S matrix. Is that right, basically?
Yes, that's right.
So is there any way of reversing this process, perhaps from a known 2D S matrix to get a corresponding 1D CFT?
No, unfortunately, this limit loses information. So for instance, you can get the same S matrix for many different CFT correlators, or families of correlators. With this limit, it drops out many terms. You can even get unitary S matrices from non-unitary CFT correlators.
So do you know any case where you get one of the integrable S matrices with no production?
Yeah. So this is what we studied already several years ago with Walt and João and Pedro and John. I think I'm not missing anyone. Indeed. So if you take the CFT correlator, which maximizes an OP coefficient with some dimension below 2 delta phi, that correlator will become basically the Sine-Gordon breather S matrix
Okay.
by this map. And you can even prove this analytically.
Right. But you can't generalize it to more complicated integrable cases.
Yeah, no, you can.
Mm.
You can have an arbitrary number of bound states. So, and this construction, since it loses information, it's easy. So if you take a general integrable S matrix, which is the product of CDD factors, then basically to each CDD factor, you can associate a CFT correlator. And then you just multiply them together. And when you take this flat space limit, you get the S matrix that you wanted.
Okay.
It's just that this is not the unique way to do it. This is one way to do it, but there will be other CFT correlators which will be sparser, which will also lead to the same S matrix. I think there the interesting question is, can we formulate the more interesting integrability conditions? They arise at 6 points. And it would be interesting to see if something like, there's some non-trivial constraints that we can impose on CFT correlators, but away from the flat space limit, that would resemble the usual integrability conditions on S matrices, so conditions of no particle production, for instance.
So there isn't a corresponding set of integrable CFTs in 1D.
Not that we know of.
Any other questions?
Can I ask one more? I don't know if you, I missed if you discussed it, but so still about this relation, the fact that the S matrix, the modulus of the S matrix is less than 1, then the avatar in the CFT is that the correlator is less than the free boson correlator?
Let me think. No, that's not true. So we can actually prove unitarity, and unitarity is the statement that on average the OP density in the CFT is equal to that of a generalized free field.
Okay, I see.
This is the statement, and we can prove this now in. So I mean, with Dalimil we had obtained some bounds that indicated this at finite delta phi, and now with Lucia and Yifei we can actually prove this also at infinite delta phi. So the statement is, I mean, it is related to the bounds. It is related. The way that we prove it in the end, we use this upper and lower bounds, and that fact that at infinite delta phi, they are basically just the same up to some exponentially suppressed corrections.
Is this statement 2D or is it true in any T? Or at least the expectation for the OP density.
So this statement applies to the SL2R OP density.
Okay.
So any CFT correlator, if you decompose it into SL2R blocks, then the OP density has to look like that of GFF. But in this process, you lose the information on how this density is distributed among spin channels.
Okay.
But indeed, the striking thing is that even an arbitrary higher D family of CFT correlators will give you something that looks like an S matrix. It's just that probably this S matrix will always be the trivial one.
Okay, thanks.
Any other questions?
But Miguel, I think your bounds do imply, just if a correlator is bounded between GFF and generalized free boson, then I think the flat space limit is going to give you a unitary S matrix now.
Yeah, but you don't want to assume that because that's too strong. That rules out bound states. What you have to show is that the bound states, they don't screw up this.
Sure.
Yeah. And this we can show, but again, we need this gap assumption. We cannot allow these anomalous thresholds.
Okay.
Further questions? I have a question about this numerics comment that you made in the end. So I was wondering how, so you had earlier proposals to use these functionals, not just this Polyakov Bootstrap, but more specific this basis of functionals alpha and beta n to do numerics.
Yes.
And so now it looks like a more specific proposal. So could you comment on what's the difference between the old proposal and the new proposal? Or what's the relation?
Well, I mean, I'm not sure. The older proposal was simply to, instead of using derivatives, to use to use these guys, these alpha n's.
Yeah.
So that proposal, I still think we should do it.
Okay.
I'm just saying that, you know, all those functionals, they are packaged together in this dispersion relation. Sorry. They are all here. Actually, you can get those functionals by expanding this equation. If you expand it for small w, you will get all the sum rules of the other functionals. So anyway, this is just a repackaging of the information, and maybe in some circumstances, this packaging can be more efficient for certain problems. Like certainly to get these bounds, we see that it is the most efficient way, right? If you want to get bounds on correlators, this is the way to do it, not to use the other bases. The other bases will take longer to converge. And also, it might be easier to work with because you just have this function of two variables, and then maybe it's easier to compute these functional actions. It might be easier to generalize to multiple correlator setup also. Maybe the functions in this case, they will be very complicated, and maybe it's easier just to impose that this dispersion relation holds.
So in the old proposal, I was supposed to take these functionals alpha and beta n, and I was considering their linear combinations. And there was a problem in practice that these alpha n's were a bit difficult to evaluate.
Yes.
And now instead of alpha and beta n, you say that I should take these other functions, which are what labeled by this label w.
Yes. So yes.
And
so now the label is w.
And so I would now, and so are these functions easier to evaluate? Like suppose that I fix the w, I want to evaluate it as a function of delta. Is it easier to evaluate than the alpha n's and beta n's? Numerically, say, or whatever, in any way.
I got these kernels numerically. The kernels themselves, I got them numerically, and then in some circumstances, I've done what you described. Like I integrate against the conformal blocks also numerically, and I get something. You know, I don't know if it will be in the end which one will be the easiest approach.
So alpha n's are given by integrating some kernel against conformal blocks.
Yes.
And these new functionals, which are packagings of alpha n, these g's, I mean, it's one of the further pages, GW or G bar W, or this one. So they're also given as integrals of some other kernels against conformal blocks.
No. The functional action. So what you're referring to is that for the normal functionals, the alphas and betas, this term is absent, and then it looks like this.
Yeah.
Here, the only difference is that there's this term, and the kernel now label.
And the kernel is what?
Whereas before it depended on whether it was alpha.
I'm sorry, I missed there was a break off. I missed the comparison.
Sorry, I said that the alpha n's and beta n's, this term would not be here.
Okay.
And this kernel, it would depend on the specific functional.
Okay.
In this case, there's this extra term, and now these guys, instead of depending on the specific functional, they depend on a choice of points.
Yeah, but I still have to do the integral. So which integral is easier, the old one for alpha n or this one for GW?
I mean, here, well, let me think. Right now, I'd say that this is more underdeveloped. Because here, you know, for general delta phi, I cannot write down this guy in closed form. The alphas and betas, in principle, I know how to write them down in closed form.
Okay.
So here, the only way I have, so you can construct these things numerically for any choice of you can construct these kernels numerically. Then you still have to do this numerical integration. You have to take this curve and plug it in here and do this integral for all delta. So yeah, there's more work. Why I think this might be pay off eventually again is maybe in considering many correlators at the same time. Maybe it will be more efficient to work with this. Basically, I mean, these kernels, they can be found basically by solving this equation. So it's kind of like a unified approach. You solve this equation and that's it. It's the function whose double discontinuity is a delta function. And this equation you can solve. This equation you can solve numerically.
Okay, I'm not sure I fully follow, but it's getting pretty technical. So are there any other questions?
So going back to this double discontinuity, it's easy to find a function with a single discontinuity given the delta function, right?
Yes. Double discontinuity is more, yeah, it's more complicated.
Right.
So yeah, these kernels, these are not trivial kernels. They depend on delta phi. For a single discontinuity, this kernel would be trivial. It's just like 1 over z minus w.
Okay. But don't you then have to find some function with a single discontinuity giving you 1 over z minus w or something like that?
So you're talking about solving this equation?
Yeah.
Now this equation you can also, even though it's called the double discontinuity, you can write it in as fixing the relation between the real part of this guy and the guy itself. So you just write down a Cauchy formula, you deform the contour, and you can use this equation to solve it.
Okay.
Yeah.
All right. Well, if there are no further questions, let's thank Miguel for a very nice talk. Thanks everyone, and see you in half an hour.
All right. See you.
Yeah.